Okay, welcome. We've made it to part three, last part of today's lecture, March 15th. So, the last thing I want to talk about in our first graph theory lecture is some standard graphs that we're going to talk about a lot. They're going to keep coming up. They're useful to refer to, so I want to define them and make sure that you're familiar with them. So the first type I want to talk about is the complete graph on n vertices. Sorry, there should really be a space in there. Graph on n vertices, which we notate k sub n, it's capital K. So if I have the complete graph on n vertices has every possible edge. That's what makes it complete. So if I look at K2, I have two vertices and I have the one edge that's possible between them. K3, I have three vertices and every possible edge between them. K4, all the edges between any two of these. And then I'll go all the way up to K5, I guess. Worth checking to make sure I got them all. If I have every possible edge and I have 5 vertices, that means every vertex should have degree 1 fewer than the total number of vertices. So in this case, every vertex should have degree 4. These are also good examples of regular graphs. So if I look at this, I can see 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Oh, but these vertices only have degree 3. That means I'm missing an edge. Now I've got K5. I can also talk about K1. No possible edges. So question, how many edges in Kn? We just finished talking about counting problems. Well, what is an edge? This isn't a directed graph. So there's just 2 vertices and an edge. And we want every possible set of 2 vertices where order does not matter, which means there are n choose 2 edges in Kn. So here n is 5, 5 choose 2 is 5 factorial over 2 factorial, 3 factorial. That's 5 times 4 over 2, that's 10. I should have 10 edges. 1, 2, 3, 4, and then 5, 6, 7, and then 8, 9, and then 10. Much easier way to count that is using the handshaking lemma. If I add up all of my degrees, I should get twice the number of edges. So if I add up 5 vertices, each with 4 degrees, that's 20. 10 edges is 10, so twice 10 is 20. Handshaking lemma checks out there. Another family of graphs we'll talk about a lot are the empty graphs on n vertices. These are E sub n, and these are exactly what they sound like. No edges. So E1 looks the same as K1, but then E2 looks like this, and E3 looks like this, and E4 and E5. A little bit easier to draw. Okay. Next, I can talk about cycles. So the cyclic graph on n vertices Cn. Here I just want a cycle going around all my vertices. So C1 and C2 don't really work. Well, maybe C1 is fine. C2 doesn't actually work if we're talking about simple graphs, but C3 is clear. That's just this. And C4 looks like this. And C5 looks like this. And in general, a cyclic graph on n vertices is a two regular graph. On n vertices. There's no handshaking lemma problem here because since I'm two regular, if I add up all of my degrees, I'm going to get 2 times n. 2 times n is always going to be even. So that's going to be okay. I can always make this a cycle. And then very similar to the cycles are the paths. The path graph on n vertices, which we call Pn. Here I have no problem with the smaller ones. Here's P1, P2, P3, P4, and P5, and so on. The path is just the cycle graph missing an edge, so that you have, once you get up to P3, everything has degree 2 except for your 2 edge vertices. Worth noting that some people, when they talk about path graphs, they use the number to represent the number of edges instead of the number of vertices, so that can get confusing. But in this class, Pn will mean the path with n vertices on it. Okay. Another type I want to talk about are bipartite graphs. So bipartite graphs are a little interesting. They're graphs where you can split the vertices up into 2 parts, A and B, and there's no edges inside of those parts. Can split or partition vertices into 2 parts, exactly 2 parts, A and B, such that there are no edges within either part. So let's look at an example. If I draw this graph, if I make my 2 parts this and this, there are no edges in between vertices in one part. This could be B, this could be A. Within my 2 parts, there's no vertices. There's no edges. There are edges between the parts, but not inside. But they don't always have to look like this. Here's a tricky example. Here's a graph. It's not immediately obvious if this graph is bipartite, but I'm going to make this including this one in the middle. Sorry. This my part A. And you can see with these 3 vertices, there's no edges going between them. And I'll make the other 2 my part B. So not immediately obvious that I can do this splitting into parts, but in this case I can. So that's a bipartite graph. And then a complete bipartite graph has these two parts and then has all of the edges between the parts. So a complete bipartite graph K, M, comma, N, again, that's a capital K, has part A of size M, part B of size N, and all edges between part A and part B. So here's K1, comma 3. One part with one vertex in it, one part with 3 vertices in it, and all of the edges in between. And here's K4, comma 2. One side has 4 vertices, one side has 2 vertices, and I add all the possible edges. Okay, and one more common type of graph that we'll see are called the hypercubes. And here the hypercubes have Q, but I'm going to use QK instead of QN. And the reason is that hypercubes don't have K vertices. They have 2 to the K vertices. The reason we use K is because the way you construct a hypercube is you list out all of the different strings, all the different ways of writing words that have zeros and ones in them, and K total length. List all K length 0, 1 strings. Those are your vertices. And then you connect 2 vertices if they differ in exactly one spot. Differ in exactly one coordinate. So Q2 I list all of the 0, 1 strings of length 2, 1, 1, 1, 0, 0, 1, 0, 0, and I connect them if they differ in one place. So 1, 1 and 0, 1, they have a different first coordinate. 1, 1 and 1, 0, they have a different second coordinate. If I change this 1 to a 0, that gives me that. If I change that 1 to a 0, that gives me that. But these two are different in 2 places. There's no edge there. And these two are different in 2 places. So there's no edge there. And why are these called hypercubes? Well, if I look at Q3, I can draw my vertices in a slightly suggestive pattern. Let's make this 1, 1, 1, 1, 0, 1, 0, 1, 1, and 0, 1, 1, 0. And then I'll make this 0, 1, 1, 0, 0, 1. Sorry, not 0 and 1. I want this to be, yes, I want that one to be 0 and 1. I want this one to be 1. I see. This one should be 1, 0, 0. That was my mistake. 1, 0, 0. This one should be 1, 1, 0. All right. Sorry, I messed that one up. Should have checked my notes more carefully. Trying to accomplish something in particular here. So this is 1, 1, 0, 0, 1, 0, and 0, 0, 0. And right now it just looks like a giant mess. But when I add in the edges, I differ by 1 coordinate here, and 1 coordinate here, and 1 coordinate here. And these two differ in 1 coordinate. And I differ, 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 and differ. And I have a cube. So I'm not going to try and draw Q4. Q4 has, well, let's see, how many different k-length strings are there? We can do a rule of product calculation. I have k places to make a decision, 2 options in each decision. I have 2 to the k vertices. So Q4 has 2 to the 4 is 16 different vertices. You basically have 2 different Q3s, and edges between them. Looks really wild, but hard to draw. Okay, one last thing I want to talk about today in this part 3 is subgraphs. So if I have a graph and I can find another graph inside of it, that's a subgraph. What do I mean by that? If the vertex set of one graph is a subset of the vertex set of another graph, and the edge set of one graph is a subset of the edge set of another graph, then G is a subgraph of H. So if I draw in a K4, I can find a copy of K3 inside of my K4. K3 is a subgraph of K4. And we use the same subset notation to mean subgraph. There are other graphs that are also a subgraph of my K4. If I pick this vertex, then this one, then this one, then this one, I can see that P4 is a subgraph of K4. Because notice, I just need the edges to be a subset of the edges. So in my original graph, K4, these 2 vertices were connected. But in my subgraph, I didn't take that edge. I just took those 4 vertices and these 3 edges. So P4 is a subgraph of K4. Now, if you want a subgraph where you have to take all of the edges, like in this K3, I took these 3 vertices and I took all of the edges that had to be there. I couldn't take this edge because its other incident vertex wasn't part of my graph, wasn't part of my subgraph. But if I just want to pick the vertices and any edges that were already there, that's called an induced subgraph. So if every edge of, I take my graph H and I restrict it to the vertices of G, what this symbol means. So I'm just using the vertices of G and I'm looking at the edges that happen if I just have those vertices is in G. We say G is an induced subgraph of H. So K3 is an induced subgraph of K4, and P4 is not an induced subgraph of K4, but it is a regular subgraph, a weak subgraph, you can say. Normally, if we talk about subgraphs, we just mean the regular type. We don't mean induced. Induced is okay, but not required. And the last thing I'll define in today's lecture is a spanning subgraph. If the vertex set of G equals the vertex set of H, then G is a spanning subgraph of H. So P4 is a spanning subgraph of K4. I'm using up all the vertices, but it's not induced. K3 is an induced subgraph of K4, but it's not spanning because I left out this vertex. And the only way you can have an induced spanning subgraph is if you take the original graph. So it's worth noting that G is always a subgraph of itself, and it is the only induced spanning subgraph. Okay, that's all for today. It was a lot of material. It comes a little bit faster because there's no time to stop and ask, talk with chat. So I apologize for that. It's a little bit of a different format. I'm much less comfortable with it. I'll be back on Thursday with regular lectures. And as always, you can ask questions during office hours and on the discussion board. So I look forward to seeing you all again on Thursday, and have a good day.